All right, so here's a cool thing with mixing. I don't know, a technique that might have some merit. This started off in a conversation on the Bitwake Discord about what would it sound like to take two Fourier transforms of two audios and then just take the maximum of each bin and then inverse Fourier transform it. So if you don't know what a Fourier is, it's this stuff. Each one of these would be a bin. What if you took two audio samples, the max of each of one of these, added them together, or the max of each one of these, and then turned it into a sound? My kind of hope and theory around it being that you don't really, the human ear isn't going to care if two frequencies overlap and become louder in terms of recognizing a sound. All it cares is that it's there. Or that also in a lot of mixing you're trying to get one frequency to get out of the other's way, and that this would maybe make that easier. And there's some success to this in what I'm seeing. So first of all, major thanks to Robbert. He basically did all the work in the end. I was working at it, like chipping away, and then he'd kind of pop in and have everything done in a really nice way super quickly. So he made this this little tool in Jupyter Lab, which is or maybe Jupyter Lab. Really cool. Basically, you go step through, upload some files, do the processing where you find which one of the bins is larger in each window, and then select all those and turn it back into a sound. Here's the sounds that I was working with that you won't be able to hear if I play here, but I'll play it somewhere else. And then the result if you do the max bin mixing, and then the result if you just add them together as one normally would. So here are the two sounds that I had. Actually, the two sounds I had are over here. And I'll just try and mute all this. There's Sorry, that's not it. It was these two. Big old kick, and a snare, and some bass, and they kind of just bounce along together. This is the raw form. You can see how it's sort of all bouncing and phasing in and out of itself, and etc. Pretty neat. So made two samples of those, uploaded them to this thing, got the result of what happens when you take the max of each bin, and then also the normal result. The overall outcome of it being these two. So let's see. This would be the frequency version, and this would be the time version. They sound pretty much the same. I was trying to check and see if there's any major amplitude differences between the two. And overall, this basically shows you which of the two has a larger amplitude on like a 10-second non-root mean follower. If you do root mean follow, it sort of changes, but the difference is less than a decibel. It's not much. One interesting thing is that the frequency one is very clean in terms of the way that it comes out, and the time one has a lot of this wobbling, and you'll see some more of that in the other example. I mean, I kind of feel like I would expect this one to have just a better overall average because of these ones peaking up high. I did try doing a really slow slope down to see if there was much of a difference, but it's still negligible. But I mean, this one does look like it's kind of pushing its limits a lot more often than this one. I'm surprised that none of these numbers are showing it, though. Maybe I did something wrong. Anyways, the cool thing I feel like about this is, I'm going to mute it so you don't have to hear so much of it, is that with like the frequency one, it's really stable. Like this is the sub bass. Here you can see the kick coming through. These are the little phasing, Reese bass type. It's just like a saw swarm or whatever on top. You can kind of, it's pretty static, which is cool, I think. And this would be the one where you do normal time mixing, where you're seeing the phases kind of mess with each other a little bit more. Maybe this is just an effect of the processing that the Fourier transform processing it went through, where it like, I don't know, got rid of some stuff, but I can't tell the difference audio wise. I mean, actually also just a little bit to me, and I might be making this up because I want this experiment to have some value or merit or something, but this sound that it's based off of, like if you listen to it, I mean, first of all, it looks, the spectrum looks more correct, but it sounds more like the sound when you mix it through the frequency method. Like, there's a lot of boy, wow, in this one that I'm not sure if, I mean, I guess it's there. It could be my ears. They're so close, it's hard to tell, but I still think it's really cool how just stable this is. Like how little, it's not jumping around all over the place. Like this one pop around all over the place. And I guess just one more thing that I think is interesting. Let's see, negative 11.3. Yeah, they're the same. They're both normalized. One more thing that's interesting is just how they sound together. It doesn't matter for anything, but it sounds cool. Not really sure what happened that it has that dee-doo-doo-doo-doo, the very tonal sound, but that is the outcome of this little experiment.